Hi guys, today we're going to be taking more derivatives. In fact, we are going to be taking derivatives for a very long time. And if you're wondering why a derivative is important for an entire math course to be based upon it, yeah, we're going to be taking derivatives pretty much the rest of the year. Just know that later on we're going to examine applications that will apply the derivative a little bit later. But for now, just trust that derivatives are important and we need to learn how to take them so that we can apply them later. Now, we have just spent the last lesson talking about the definition of derivative, and I gave you this limit definition. And this is the definition of derivative. This is how you can calculate a derivative for any function. But it is a cumbersome limit process. It's a lot of work. So today's lesson is going to be all about showing shortcuts so that we can do derivatives in our head without having to write all that limit work down. So let me show you what I mean. We're on page 32 in your notes packet. We'll come back and do example 1 first, but I think the best example is a little bit further down. So I'm going to look right here. So we'll talk about the power rule in just a second, but what I want to do is I want to look at this function y equals x squared and the work it takes to calculate the derivative if you use the definition of derivative and the limit process. So if I use the limit process, then I've got to start here and then do some algebra and then factor out an h, then simplify and then substitute 0 in for h and get 2x. Yes, we can do it, but who wants to do that 1, 2, 3, 4 more times on this line and then for all the other problems on the page? No one. No one wants to do this. So we need a way to be able to jump from here to 2x. If you are seeing it, awesome. If not, here it is. Here's how you take a derivative of something that looks like a polynomial, like a single term. If you have something like y equals x squared, what you'll do is you'll take the exponent and you're going to bring it down into the front and multiply it by whatever number is in front of that x there. So if y equals x squared, then dy dx equals 2x. Done. We can now do it this way. We no longer have to do, let me erase all this. We no longer have to do the definition of derivative anymore. In fact, I'm not going to make you do it anymore in a test either. You've already showed me that you can do it. We are done with definition of derivative. It's gone. It's over. And so now you can appreciate this method. So let's look at the second example. I won't use the unicorn pin the whole video. I know it's probably hard on the eyes. Okay, f of x equals x to the 6th. So I need to find the derivative. So I'm going to take this exponent, bring it down to the front. F prime, or the derivative of x, equals 6x. And I will subtract 1 from the exponent, 6x to the 5th. So the power rule, what the power rule does is you take the exponent, you bring it down to the front, and then you reduce the exponent by 1. So here's what that is saying. This is the power rule, official mathematical power rule. The derivative of something to the n power, you bring the exponent down and it becomes the new constant, and then you reduce the exponent by 1. Example C. S of t equals t to the 30th power. So then s prime, or the derivative, I will bring the 30 down, 30t, and I will subtract 1 from the exponent to the 29th. So s prime of t is 30t to the 29th. Done. Now, part D, we can still apply the power rule, but we need to change the way that it looks, because in order to apply the power rule, we need it in this form where you have something raised to a power. So we can rewrite it because the square root of x is the same as x to the 1/2 power. Because if you remember, whenever you're working with radicals, what's on the denominator is the type of root you have, and the numerator is the exponent on what's inside. So y is the same as x to the 1/2. So then dy dx, or the derivative with respect to x, is 1/2 x to the negative, I subtract 1, so 1/2 minus 1 is negative 1/2. So you can leave your answer like this, or sometimes you'll be asked to write your answer with a positive exponent. So this is 1/2 times 1 over x to the positive half, because if you have a negative exponent, it goes to the denominator. Then I can write that as 1 fraction, 1 over 2x to the 1/2. And x to the 1/2 is the same as a square root, so this is 1 over 2 square root of x. Now, any of these answers are fine. So you could write your answer like this. You could write your answer like this. And you could write your answer like this. I would accept any of those answers on a paper assignment. Sometimes you're given directions to write your answer with a positive exponent. Sometimes you're asked to write your answer as a radical. Sometimes you're given a multiple choice question and you have to determine which one is your answer, and you don't know which way that they're going to write the derivative. So you just need to be careful, or be able to realize that if you get this as your answer, it's the same as that. So it's one frustration that calculus kids have a lot, because if we're doing questions in the book, they're like, my answer doesn't match what's in the back of the book. So you have to know, is your answer equivalent to the one that's given? If you ever have a question with that, you can always email me or let me know, and I'll work with you on there. So in general, though, we prefer to leave our answer with positive exponents. So let's look at examples E, F, G, and H. Now, before I can take a derivative, remember, I want it to be written in the form y equals x to the n power. So I need it written like this before I can take a derivative. Let's see. So y equals 1 over x. That is the same as x to the negative first power. So my derivative, dy dx, is equal to, I'll bring the negative 1 to the front, negative 1 x to the negative second power. But I need to write it with a positive exponent, because that's what I'm told to do right here. So negative 1 over x squared. F says 1 over x cubed. Purple. So 1 over x cubed is the same as x to the negative third power. So then if it's x to the negative third power, then f prime of x is the same as negative 3 times x, subtract 1, to the negative fourth power. So f prime of x is negative 3 over x to the positive fourth power. Then sometimes you'll have some with radicals. So this is a cubed root, which is the same as 1 over t to the positive third. But again, I need it written as x to a power, not 1 over x to a power. So this is the same as t to the negative 1/3. So now it's in the form that I need it. So then s prime of t is going to be equal to negative 1/3 t. If I subtract 1 from 1/3, I get negative 4/3. So then if I write it with a positive exponent, x prime of t equals negative 1 over 3 t to the positive 4/3. And then letter H is a lot like F, so we can skip that one for now. So then if you look at the constant multiple rule, that deals with if you have a constant in front of a function. So something like 2 over x squared, which I can rewrite as 2 times x squared. So again, I need it in the form y equals x to the n power. I want it to look like a polynomial or a term that would be in a polynomial. And this is an x squared. This is x to the negative second. Okay, so then let's see. If I want to find the derivative, that would be dy dx equals. Now there's a constant in front, and I'm not used to having that. That's not how we did the previous examples, but this is the constant multiple rule. If there's a constant in front, you'll multiply the exponent times what's there. So negative 2 times 2 is negative 4x to the negative third power. Subtract 1 from the exponent. Now I'm going to leave my answer like this just to make sure we understand the constant multiple rule and not get lost in the negative exponent part. On the next one, we see that f of x equals 4x cubed over 3, which is the same as 4/3 x cubed. So when I apply the constant multiple rule, this is f prime, so be careful with your notation. F prime, I'm going to multiply 3 times 4/3 and get 12/3 x squared, because I subtract 1 from the exponent, and then 12 divided by 3 is 4. So f prime of x equals 4x squared. Now when you're doing these, make sure that you are labeling the derivative as the derivative, not as the function, because the function is the original problem. The derivative is an entire new function. Let's see. Let's look at problem H. There we go. So problem H is 12 over the cubed root of x to the fifth, which is the same as 12 over x to the 5/3. But again, I need it written in the form x to an n power. So I need like a constant times the x. So 12 times x to the negative 5/3. So when I go to find the derivative, dy dx, I'm going to multiply negative 5/3 times 12. Get negative 20 x, and then I'm going to subtract 1 from negative 5/3. I get negative 8/3. So let's look at a couple problems that you'll have like this on Delta Math. Here's an example. You have the equation f of x equals 9x to the fourth, and I need to find the derivative. So I'm going to multiply 9 times 4. I get 30, oh no I don't, 4 times 9. Yeah, 36 x to the third power. So I'll type in 36 x to the third. Answer, yes. Now, now look back up at the top of the page when we're talking about derivatives. Now let's talk about constants, because you might have something that just says y equals a number and then you're asked to find a derivative. So we can do this the same way, but if you think of this as being y equals 9, and if there's no x here, I could say that's the same as y equals 9 times x to the 0 power, because anything to the 0 power is 1. So I haven't changed what this means. I just changed the way it looks, because really I have 9 times 1, which is 9. But to be able to take the derivative, I need a constant times an x. So I'm writing it like that just to illustrate how this works, because we can do it the same way. So if I were to apply the constant multiple rule, I'd multiply 0 times 9 to get my derivative, dy dx. 0 times 9 is 0, x to the negative 1, and anything times 0 is 0. So the derivative of 9 is 0. And that's the constant rule. The constant rule says the derivative of a constant is 0. It's always 0. no matter what. So it's really nice when you come across a constant like f prime of x equals 0. If that's a constant, or f of x equals 0, derivative 0. S of t is negative 8, derivative 0. Ooh, this one looks crazy, but pi is a constant. So dy dx equals 0. Now, one that people like to throw in there, y equals e squared. Well, e is another constant, so dy dx is 0. Let's see. So I pulled this problem over from Delta Math. Now you're given f prime of x or f of x equals 5. It's a constant, so the derivative would be 0. Yay! Okay. Now, whenever there's a single variable, like a variable without any exponent on it, keep in mind that the exponent, if there's not shown, it's understood to be a 1. So I can still apply that power rule. Dy dx equals, bring the 1 down. So 1 in the front would be 1. X, subtract 1 from the exponent, I get 0. And anything to the 0 power is 1. So this is 1 times x to the 0 is 1, and 1 times 1 is 1. So the derivative is 1. The derivative of x is 1. So if you just have an x or just have a variable, the derivative will always be 1. So we're going to take that information and we're going to add it into combination with the sum or difference rule, which is really just saying that I can take the derivative of each term individually for an entire string of polynomials. So dy dx here, derivative of x squared is 2x, derivative of 5x is 5, and the derivative of 3 is 0. So the derivative with respect to x is 2x plus 5. For b, it looks not long and scary, but I just take the derivative of each individual term. So the derivative of x to the 4th, bring the 4 down, subtract 1 from the exponent, 4x cubed, minus 3 times 3 halves is 9 halves, x squared. 2 times 2 is 4, so plus 4x, subtract 1 from the exponent, 1, or just x. The derivative of just an x is 1, and the derivative of 6 is 0. Now, in order to apply this derivative technique, you need a long string of polynomials. Because this process only works whenever the function is set up like this. So if you come across something that's a binomial squared, you're going to need to go ahead and rewrite that binomial. So I'm going to go ahead and square that. So y equals 4x squared minus 6 minus another 6 would be minus 12x plus 9. Then I can take my derivative. So 2 times 4 is 8x minus 12. Now notice I'm careful with my notation. When I'm just simplifying, when I'm just squaring, this is still y. I didn't use the dy dx notation until I switched over to the derivative. So just be careful with that. Then you'll have some that you'll need to rewrite as a long string of terms, because we want everything to look like a polynomial. It may not be a polynomial, but we want it to look like a polynomial as close as possible. So if you've got things in the denominator, just a single term, you can rewrite them with negative exponents. So the 4 over x is the same as 4 times x to the negative first. 4 over x squared is the same as 4 times x to the negative second. And 4 over x cubed is the same as 4 times x to the negative third. Now I can take the derivative, or another way to say that is to differentiate it. So dy dx is negative 4x to the negative 2 plus 4x to the negative 3 minus 12x to the negative 4. I'm just checking my work. Yes. E is another example where we could rewrite this. So I'll distribute the 6 square root of x. 6 times 2 is 12. Square root of x times square root of x is x. And then 6 times negative 3 is minus 18 square root of x. And square root of x is the same as x to the 1/2. So I have not taken a derivative. I'm still rewriting the original problem to the positive 1/2. Now that it's rewritten, I can go through and take my derivative. F prime of x, exponent is 1, 1 times 12 is 12, minus 1/2 times 18 is 9x to negative 1/2. Or if I were to rewrite this with positive exponents, f prime would be 12 minus 9 over the square root of x. And no, you don't have to rationalize the denominator. You can, but you don't have to. You did enough of that in Algebra 2 and Pre-Cal. So here's an example of something like you would see in Delta Math. Y equals negative 2 over the cubed root of x to the 5th. You'll want to rewrite this. Y equals negative 2x to the negative 5/3. So then the derivative dy dx would be positive 10/3 x to the negative 2/3. I'm just double checking my math. Negative 2 times negative 5/3 is 10/3. And negative, I subtracted incorrectly. Yes, negative 5/3 minus 1 is negative 8/3. Then it says, write your answer in radical form without using negative exponents and simplifying all fractions. So this would be 10 over 3x to the 8/3. And they want it in radical form. So that would be 10 over 3 times the cubed root of x to the 8th. But then it says simplifying all. I probably need to simplify this because I could simplify this by dividing 8 by 3. So 10 over 3 cubed root, let's see, 8 can be divided by 3 twice, so x squared, and there would be 2 times 3 is 6, there'd be 2 left over. So let's see if this is how they want me to type in my answer. Times cubed root of x squared. Can't get to the yes button. There we go.